So today we're going to be doing a little bit of integration, another video about integration, and we're going to be doing it on integrating arctan of something. And the reason why I'm using this integration is because we're going to do two substitutions, plus an integration by parts. So it's just when I was doing my homework today, I was like, how's this possible? I've never seen this before. So I wanted to make a video about it. Basically, you can do multiple substitutions within one kind of solution, and that's what we're going to be seeing. Okay, so we have this equation here where we have the integration of -2 arctan bx plus c dx. It doesn't matter what these are. We're going to find the kind of general form of this indefinite integral, and whatever it is, we can sub in later. But we're trying to solve this. And so first steps first, we're going to take -2 out, and we have arctan here, bx plus c dx. Now, arctan is one of those things that just cannot be integrated. Like if for example, if I did arctan integration, right? It's not going to come up with anything. Actually, it does. It's okay. It's okay. Doesn't matter. Most important thing is arctan is one of those things where it's like it's very, very, very annoying to integrate. And you'd rather do differentiation with arctan. Arctan differentiates into 1 over 1 plus x squared. That's the preferred way to kind of solve arctan. And so how are we going to do a situation where even though we're integrating arctan, we get to differentiate arctan, right? Arctan is easier differentiated than integrated. Well, what we could do is we could use integration by parts, because remember, one of them, let's say that it's 1 multiplied by arctan, then in this case we can take 1 as u dash or v dash, and then we integrate that, and then arctan gets differentiated. So there is a way to differentiate arctan. And this is the same thing for any other expression where you'd rather differentiate it compared to integrate it. So we'd rather differentiate arctan. But obviously, there's this complicated thing here, and it's going to kind of just mess up with the way that we do the equations. If we do it out, it's going to be like 1 plus bx plus c over, like, there's going to be like an x here, or like bx here, whatever, right? It's a mess. And so the way we're going to do this is going to use first substitution. We're going to use first substitution. We're going to let u just clean up this, and this is a general kind of, if we want to use substitution, we can. And the way we want to use substitution here is we want to say let u equal bx plus c, right? Why can we use this substitution? Notice that usually we have something that differentiates, into this so that we can get that with dx and turn that into du. But why can we do this? Well, because this one, if you differentiate it, it only turns into a constant, which in this case is b. And it's always simple to multiply the expression by that constant over itself. So you're not changing the expression because you're multiplying by 1. B over b is 1. But then you can get substitution. So here's another point. If you ever see a situation where you can choose a substitution that differentiates into a constant, you can use that as a substitution. No matter whether there's something else that differentiates into that, if it differentiates as a constant, it's very simple to substitute into it. So let's do this. We're going to let u equal bx plus c. Then du, which is simply the b dx. Okay, now let's write the equation again so that it's the same thing, but then it contains b in it. So arctan bx plus c, and we're going to multiply by 1, but a special type of 1, b over b, that's 1, dx. So we see this part here, that's equal to this, right? And so we can put du into there. So let's rewrite the equation. -2 arctan, integration of arctan, bx plus c, times 1 over b du. Does that make sense? We took that b and dx, turned it into du. This means we can take this b out and bring it here. There we go. And now, if we rewrite this with u substitution, it would be arctan, arctan u du. Okay, it's a lot simpler now. But remember, we still don't want to integrate arctan. Integrating arctan is a pain. We'd rather differentiate it. And so what we can do now is we can say this is, hey AJ, I'm just recording a YouTube video right now really quick.
Drawing.
Yeah. Nice. Clean. Oh, you're drawing outside?
That was like 6:21.
Alright, so that was just my roommate, guys. But anyways, we can pretend that arctan is being multiplied by 1, and therefore we can use integration by parts to solve this, right? So we have, let's say that our v dash in this case is equal to 1. Therefore, the integration of 1 is x. And now we get to say that arctan is equal to u. arctan is equal to u. And so now we get to differentiate arctan. Arctan differentiates into 1 over 1 plus, we can see here, x squared. In this case, it will be u squared. And there we go. Now we have the different components. This is going to be equal to uv. So v here, arctan is x arctan, u. Oh, sorry. I forgot to say something. So when you have it in terms of u here, 1 doesn't integrate into x, it integrates into u. That's my bad, guys. So then the expression here would be equal to u arctan u minus the integration of u dash multiplied by v. So we have u multiplied by 1 over 1 plus u squared du. Okay, now let's clean this up. And this is another reason why I wanted to make this video, was I didn't know that you could make integration by parts when you already have substitution. It's really interesting. Okay, so now we have u over 1 plus u squared du. Okay, this is tricky, right? Oops. This is a very kind of tricky expression, and we don't really know how to integrate this. But notice this. This expression in the denominator, what's that differentiation? D over dx of this would be equal to 2u, which is just a constant multiplied by the denominator, right? So, numerator, sorry. So what we're going to do is we're going to do another substitution. We're going to say let's use a different one. Let w equal 1 plus u squared. Therefore, dw equals 1 plus, equals 2u du. Okay, so now let's rewrite this integration here, this one. Let's rewrite that one into a form with 2 in it, because we want to have 2. So now we have u over 1 plus u squared. Let's do 2 over 2. 2 over 2 is just 1. We're not changing the expression, but we do end up with 2 in it. Now this one can be turned into dw. So now what we're going to have is the integration minus integration of, sorry. This one is what's going to be substituted for dw. And so what we're going to have now is the minus integration of 1 over, remember that 1 plus u squared is w, 1 over w. This, okay, so that's all going to be dw, and that's 1 over 2. We're going to take this 1 over 2, we're going to put it outside. So 1 over 2, the integration of 1 over w. That's simple. That's just the half of ln w, right? ln w. And if we remember to substitute w was equal to 1 plus u squared, and so this is now equal to minus 1/2 ln of 1 plus u squared. So let's put this all inside one equation. So now we have u arctan u minus 1/2 of ln 1 plus u squared. And now it's just a simple act of having to substitute our original u, which is bx plus c, into it. So now we have u here, bx plus c, multiplied by arctan bx plus c minus 1/2 ln of bx plus c. And there we go. All right, thank you guys for watching so much. It was just really interesting, concept of being able to do both substitution and integration by parts, and then substituting again, which I thought was really interesting. Want to note down. Thank you guys so much.